Hi everybody, I said that the next video was going to be about solving some problems, but I think that it might be better if we went ahead and injected in the Henderson-Hasselbalch equation here, because it is kind of a shortcut that again lets us bypass some of what we'd be doing in the ice table, and I think it actually makes the problems that we were going to solve easier, and so I don't really want to teach you the long way to do a problem if it makes more sense to use this shortcut and this assumption. So we'll go ahead and talk about the Henderson-Hasselbalch equation. Okay, so the Henderson-Hasselbalch equation is going to refer to our buffer situations. So when we have these buffers, we're assuming that we have a weak acid and its conjugate base, or a weak base and its conjugate acid, so there's not a lot of dissociation that's occurring. So inherent to using Henderson-Hasselbalch is this idea that we need to make sure that we have just a little bit of dissociation, right? We have to have a Ka that's small, or a KB that's small, so that we can really kind of ignore that X, right? When we were doing, the original concentration of acid minus X, we want to be able to use the 5% rule here. So the equation that we're going to use is pH, which a lot of these questions have been asking us to calculate the pH. The pH in this buffer system is going to be the pKa plus the log of the conjugate base, that anion of the acid, divided by the concentration of the starting acid. And so the thing here that you haven't seen before is pKa. So what is pKa? You see that P, we've already had on an exam, that P is going to be related to that mathematical operation of taking the negative log of whatever comes next. So if you see a pKa, that is saying put a Ka inside there and then take the negative log of that. So that means that the Ka is going to be referring to whatever's dissociating, and we'll take the negative log of whatever's dissociating, it's Ka, and stick it into this equation. Alright, so we'll go ahead and use the exact same example we left off with in the previous lecture, so we can just use this Henderson-Hasselbalch equation to solve that same problem and show you that we get the same pH. Alright, so you saw this already. What is the H3O concentration and the pH in a solution? 0.25 molar acetate, 0.030 molar sodium acetate. We solved this already. We got a pH equal to 3.82. So let's make sure that using this equation, this Henderson-Hasselbalch equation, we're able to get that same answer. So here's the equation that we want to use, and so now it's just a matter of figuring out which parts are going to go into this equation, because we are in fact asked to solve for pH, and that's exactly what we're solving for with this equation. So the initial acid, we're talking about what is the concentration of this species. We want to know about the anion that is the result of deprotonation. So that's going to be this, right? This is the A minus. This is the anion that's left over after the acid dissociates. And then the Ka, so we've got a Ka here. And so we're going to need to put that into the equation here and take the negative log of it. So we can go ahead and start to fill in these parts. Our pH is going to be the negative log of that 1.8 times 10 to the minus 5. Then we're going to add that to the log of the ratio of 0.30, because that is the anion. That's how much has been added. And then it's going to be the divided by 0.25, because that's the original concentration of the acid that came in. So we can go ahead and start to simplify. So that negative log step gives us a pKa of 4.74, and then we're going to add it to the log of that ratio, which was 0.12. We get 4.74 plus a minus 0.92, and so that's going to decrease the pH, and so when you do that subtraction, 3.82 is what you get, and that is a pH, and that is consistent with what we got last time doing it the long way with that ice table. So again, this is going to represent a shortcut for us. Okay, so now we'll do another example. I realize the example numbers are backwards, but that's because I wanted to organize them to flow from the previous lecture into this lecture. So this is just another example reminding us the normal pH of human blood is around 7.4. There's a system in place in the bloodstream, and that is the carbonate buffer system, and it's actually going to draw upon the carbon dioxide that we already have access to. So we are making carbon dioxide when we do cellular respiration. It's a byproduct of the glucose that we eat. And then, of course, our blood contains plenty of water, so that's where the water is coming from. And so when that carbon dioxide is dissolved in the water in our blood, it forms a compound, and that compound is H2CO3. So that is going to be carbonic acid, so that's the name of H2CO3. And so carbonic acid is a weak acid, and it's going to dissociate. And when it dissociates, we're going to end up with hydrogen carbonate, which is an ion, and we're going to end up with the H3O that we expect to have when an acid dissociates. Now they want us to use this balanced chemical equation to answer a question. If they give us a starting concentration of carbonic acid, and they give us the concentration of the anion of that acid, then what they want us to do is to figure out the pH. Now, we're going to need the pKa of carbonic acid. It's not given here. It's in Appendix H at the back of our textbook. I did go ahead and type it in on this slide, so when we go to solve this now, you'll have the Ka in front of you. So let me go ahead and write the Henderson-Hasselbalch equation. And before we go much further, we should go ahead and check to make sure that the approximation, that 5% rule, looks like it's going to apply. So we're going to look at the Ka. The Ka up here is going to have some number times 10 to the minus 7. So that minus 7 says only a little bit of stuff is going to dissociate. And so we realize that the 5% rule started to break down around 10 to the minus 3, 10 to the minus 4. When we're 10 to the minus 5 and kind of above, then it seems to be much more appropriate to use that 5% rule. So 10 to the minus 7, we should be in good shape. So we will go ahead and proceed using the Henderson-Hasselbalch equation, which requires that 5% rule be in place. I can start thinking about what information from the problem is going to be appropriate for entering into this equation. I have my starting acid concentration. That's going to go down here. I have my anion concentration, the conjugate base concentration, that's going to be going in the top. I have a Ka. That Ka value here is going to be important for me calculating a pKa. So I can go ahead and start to enter that information. I can go ahead and start to simplify that. I can simplify it further. And so my final answer here is that the pH of blood in this example is 7.67. So that's kind of in the ballpark of what we're expecting. We can see a pH around 7.4. We can see deviations in that pH of somewhere between like 0.1 and 0.4. So we're not quite up to 7.8. So this seems like it's reasonable for an answer based on what we saw in a previous lecture about where the blood pH ought to be. So again, this simplifies it. You saw we didn't have to do any ice tables so long as we meet that assumption being that this is not going to dissociate much, so we can forget about that minus x or plus x component. And so we can use this shortcut when we solve that long problem that I referred to in the last lecture. And so if you want to go ahead and close this one, we can move on to that longer problem that hopefully we can make shorter by utilizing this shortcut.